del Instituto de Matemática de la Universidad de Río de Janeiro. Él nos va a dar esta charla de Gromov Hausdorff, Stability from Unmeasurable Viewpoints. Profesor, adelante.
¿Están viendo mi pantalla?
Sí.
Ok. Todo el asunto aquí es para darle publicidad a este libro que va a aparecer. Yo le quiero dar publicidad a ese libro.
Escribieron un libro.
Sí, vale. ¿Ah?
Chuta.
Dale publicidad a ese libro. Yo le quiero dar publicidad a ese libro. Va que me vuelvo rico. Ok, vamos a ponernos serio, pues. Ok, yo voy a dar la charla en español, pero va que se me aparece alguna palabra en inglés o portugués. Todos me disculpan, anticipada disculpa. Este es un trabajo en conjunto con el profesor Lee y TAC, que es el Marcelo Viana chino. Este chamo aquí, este chamo presta. Ok. El título es Gromov Hausdorff Stability from a Measurable Viewpoint. Todo el asunto aquí gira en lo siguiente. Arbieto fue el originario de esta definición de la estabilidad segundo Gromov Hausdorff. Fue Arbieto, el culpado fue él. Él llega y se me aparece un día, chivo, ve acá. Ok, si hay algún peruano chivo en Venezuela, no es aquello que están pensando. No te rías, Bernardo, que me pone nervioso. Entonces, el Arbieto se me apareció un día diciéndome, ¿qué tal si perturbamos Gromov Hausdorff? Entonces yo no lo entendí porque yo no sabía realmente de qué estaba hablando. Pero entonces un tiempo después me di cuenta de lo que estaba hablando y ahí lo tomé a serio. En fin, el Arbieto es el culpado de eso, de la estabilidad segundo Gromov Hausdorff. Ok, y aquí el asunto es verlo de una manera, de un punto de vista mesurado. ¿Qué significa eso? Bueno, es otro libro que estamos escribiendo entre Lee y TAC, que es acerca de cómo se puede ver un sistema dinámico de manera mesurable. No estoy hablando de ergodicidades, no estoy hablando de mesure preserving, nada de eso. Pero en fin, eso es otra cosa que otro día hablo. Bueno, aquí la introducción es la siguiente. Ok, voy a hablar en inglés porque aquí a veces voy a tener que leer. ¿No? A paradigm dynamical system is this, stability. Roughly speaking, a dynamical system is stable if the behavior prevails under small perturbation. Okay? This idea have many branches in like structural stability in differential dynamics or topological stability in the topological sense by Walters. Ok, maybe, puede ser que Víctor haya conocido a Walters. Yo no sé si lo conoció, pero en fin.
Sí, me dio clase.
Está vivo, y está vivo, ¿no?
Pues no sé, creo que sí, debe tener 80
Está
años.
vivo, ¿no? No apareció por ahí un congreso obutari, ¿no? ¿Cómo es? Nada de eso, ¿no? Está vivo. Ok, we can also, okay, this is the stability segundo Gromov Hausdorff. Ana Vieto and I introducing in this reference too, where not only the map, but also the space is perturbed. Okay, measurable version I will consider later, but an ancestor of our definition with Arbieto is Fukaya. This comes from geometry. In geometry, what Fukaya did was this: he perturbed the Laplacian in a manifold. Okay, and he analyzed the first eigenvalues of the Laplacian under perturbation, which he called Gromov Hausdorff perturbation. And he also need to consider the measurable sense because he also considered the perturbation of the measure. And this is one of the points I will talk here. Okay. Okay. Next appeared our definition with Arbieto, which was generalized for flows, finitely generated group action, and recently, maybe in the future, will be to random group action and so on. Okay. For two measurable version are the topological stable measure in the evaluable sense. This is my paper with Lee, Professor Lee. And now recently we introduced this definition, which I will not talk today, but it is very interesting also, which is a mu topology stability. Okay, in this lecture, we are going to analyze topology stability from the measurable perspective. Okay, freeze. Okay, I will talk about. Okay, this is first we introduce a measure depending distance between continuum and compact metric space, and then we prove that this distance define a quasi-metric in the space of measure preserving symmetrically conjugated classes of continuous map. Okay. Now, after that, I will consider this the distance. With this distance, I will define a mu topological Gromov Hausdorff stability for maps, where mu is a border measure, a border probability measure of a compact metric space. And then I will prove that I will construct many examples of mu topological Gromov Hausdorff stable maps using a Walter's tie stability theorem for this case. This is the content of this sentence. Okay, let's go to the statement or the result. Okay, we'll start with everything here is topological. I mean, it's a metric, compact metric space. The way to push to topological spaces have a trouble here because it's not easy to define isometries in topological space without metrics. It's possible if you consider a uniform space by using the pseudometric, but in general, a space topology space is not necessarily uniform. Okay, the node, but the identity, okay, this is the C0 distance, this one. Okay, now I will introduce the notion of topology stability for Walters. And continuous map in a compact metric space is topologically stable if for every epsilon there is delta, so that any other perturbation close to delta close to F, you can in some sense conjugate. This is the conjugation you will get, and the conjugation is required to be close to the identity. Okay, the conjugation is only a semi-conjugation in the sense that it's not invertible. Okay, this is a big difference with the structural stability, where the conjugation is required to be invertible. Okay, now we are going to see this definition from a measurable perspective, and then we start with Borel sigma algebra. Everybody know what is that? What is a measurable maps between measurable space? If you have this. Okay, the preimage of a Borel set is a polar set also, and a polar probability measure is a sigma additive measure giving one in the space. Okay, this is the space of Borel probability measure. This, and if you have a measurable map, you can push forward a measure with this formula. With this formula, which are trying to separate, but okay. And we are going to say it's invariant if it's a fixed point of the pushboard operator. Okay. Now I will introduce the definition of mu topology stability, which I will not go to develop here. Maybe we will include in this investigation, but give to us some interesting results. Then I would say that if F is mu topology stable when for every epsilon there is delta, when F and G are delta close, then there is a compact G invariant set X prime in X with big measure. And this means that the measure of the set is very big. It's a big J invariant set and a continuous map making the conjugation, but restricted only to the big set. And also we require the distance between H and the inclusion be less than epsilon. Okay, another variation of topology stability deals with perturbation. Okay, I will now introduce the situation of the Gromov situation where you perturb also the space. Then given an epsilon necessary continue. Now I will enter in that matter. I will explain how to perturb the space. And given epsilon, I will define this object, which is called epsilon isometry. character. This means here that it's an excellent isometric immersion. I mean, the difference between the image and the pre-image in terms of distance is less than excellent. Okay, this means that he preserved distance within epsilon, and also required this is epsilon onto. I mean, this part here means that the y you can put some x less than distant epsilon from the image set. Okay, and isometry will be characterized as a zero isometry. Then we can allow here this epsilon to be 0. Okay, and then the Gromov Hausdorff distance between x and y is defined as the infimum of epsilon, for which there are epsilon symmetry from x to y and vice versa. Okay, I will not enter in details about the Gromov Hausdorff space, which is the space of compact space endowed with this distance. There is a lot of theory. I will not talk about that. I will refer the book to Burago Ivanovich for details. Okay. For mark this definition, I will transform this definition now for maps. The definition for maps is this, giving the C0 Gromov Hausdorff distance between maps F and G is the infimum of epsilon, for which there are epsilon symmetry Y and J, satisfying the relation. This says to you that they are most conjugate. This is a most conjugation. It's a conjugation within epsilon, and also for J. This part is not so necessary. Indeed, this part is not so necessary. What is important is the other part, and because we can reduce the convergence to only this part. Okay. But this is the complete definition. We put the both because we need metrics usually to be symmetric, and that's why these parts are added. Okay, with this definition, we are going to, there is a type of stability with Arbieto told to me, and I developed it with him, a continuous map, compact space, topological GH stable. I mean, GH means Gromov Hausdorff. If for every epsilon there is delta, so that if F and G are within delta, but in the Gromov Hausdorff 0 sense, then there is a continuous epsilon isometry, making this conjugation. Okay. You note here that the isometry, the epsilon symmetry is first of all continuous, and second defined in the whole space at y. Okay, the continuity here is very interesting because epsilon symmetry usually in the theory of a Gromov Hausdorff topology, this is one not required continuity, but here continuity is some very good thing to deal with. Okay, now we now see this definition from a measurable perspective. Then this is now I will enter in the main topic of the lecture, which is going to transform this definition a measurable one. Okay, the total variation. Okay, this is the total variation distance between measures, which is very famous among statistics. This is the equivalent of the, you see, the weak star topology. It can be seen as the strong topology in the operators, in operators. But the total variation can be seen as the operator theory, operator norm. This is the equivalent between both. Okay. There are another equivalents which I will not talk, but this is very simple. You see, this compare the measure from the scratch. I mean, comparing Borel set by Borel set. I mean, the distance is the supreme of the distance. This supreme is, of course, if not bigger than one, because the measures are supposed to be probabilities. Okay, this distance permits to define measure zero Gromov Hausdorff between maps, and this is the idea. Okay, now I will consider two maps, F and Y and G. But also in the space X and Y, they are also measure mu and measure mu. So I will consider the space together with a metric and a metric space together with a measure. which is popular. This is the name of popular name of a measure metric space. Okay, I will assume they are compact, and then I will define this distance in red, depending on mu and nu, as a infimum for which this whole topic realized. Okay, this is a almost conjugation. This is the Gromov Hausdorff part. However, here appear a new ingredient, which is this phrase that essentially that the E star, I mean, the push forward mu will be quite similar to mu, and vice versa. This part is added because we need a metric to be symmetric. Okay. Now I will use some property of the distance. This distance. Okay. First of all, I will put the traditional definition, which are measure preserving isometrically conjugated. If there is an isometry which preserves the mesh, preserving isometry J between Y and X, doing this conjugation. This, okay, I am requiring not only to be measure preserving, but also isometric and isometry. So I this preserve not only the measure, but also the distance. Okay. Okay, the theorem here is this. This is a list of properties of the distance. I have to check this theorem because we require to see what is the structure of this distance. First of all, this is the distance between two maps is 0 if and only they are F and G are measure preserving isometrically conjugated. I mean, fall in this definition in red. Okay, second, the Gromov Hausdorff distance between F and G is less than or equal than this distance for every mu and for every mu. The third is the distance is symmetric, but the symmetry. Okay, there is a small a little mistake here because I need to permute nu and mu here. Okay, this is a mystery. Okay, and the 4 is the triangle inequality, except that here appears number 2. This is not so serious. You can still define a topology even those situations are metricsable. So it's not so serious problem. Okay, and then definition of a measured C0 Gromov Hausdorff distance between maps F and G is defined as the infimum MGH0 for which there are this kind of conjugation. Okay. The difference here is that you have measurable isometries instead. You don't. The difference with the other. When you eliminate this M, then you eliminate the measurable here, and then you recover the Gromov Hausdorff distance between F and G. Okay. The topology is induced by DMG0 and DGH0 are in the space of continuum map of metric space is the same. I mean, those are topologies that the same. This gives to you the same topologies. Okay, item 3 of theorem 1 implies this. You have this infimum, and this is a kind of a variational principle, which indeed you get equality in certain moments. Here you don't get inequality. I don't know if the equality is true indeed, but you don't get inequality. But because you are using the total variation distance between measures. But if you change to another measure, a distance between measure like a Wasserstein distance, or even the Prohorov distance, Prohorov, you can obtain the equality. This is a variational principle we are going also developing. Okay, now we are going to introduce the main definition of this work, which is the definition 8. Definition 8, they say that we are transforming now the topological G established into a measure. Now you put a measure and ingredient, and this is the definition. Distance between the map is small, you get a big set Y prime, very big in measure because of this identity, this inequality, and a continuous isometry from Y prime to X doing this conjugation. Okay, now a stupid remark here is this. I mean, the stupid remark here, I will try to separate. The first is that every topological G-stable map of compartmented space is mu topological style for every mu. This is the first, and the key point of measurable version is this. Okay, I will try to explain what is the idea of the measurable setting. You see, this is the definition which is deterministic. No measure is involved in definition. And in the second part, there is a second definition where measure is involved. So the idea is this: the deterministic property, which is this one, the deterministic property implies the measurable property for every mu. Okay, this is similar to the topological entropy. You see, the topological entropy is supposed to be the supremum of the entropies of the metric entropies over the whole probability measure. Then this is a kind of you don't have supremum, but you decompose a definition which is deterministic. You decompose into definitions which are measure depending on the measure. And now the problem is to see if the converse is true. Suppose every mu, the map satisfied that this is mu topological G-stable for every mu. Then the problem is to see if this map is topological G-stable. But you can consider this question. I don't know the answer yet, but you can consider this question not only for topological G-stable, but with on another properties like expansivity, like shadowing or equicontinuity or the others. So this is the way, this is the reason we are talking here about measurable viewpoint. This is the key of the measurable viewpoint philosophy. Okay, to transform a property of a dynamical system, a deterministic, into measure depending definition, and then try to see if the measure definition, depending definition, recover your original. First of all, your deterministic definition implies the measure preserving the measure definition, and then you try to recover the converse. If the measure depending definition for all mu implies that you have the property for the deterministic property. This is the philosophy behind, and you can apply to many authors. This is the idea of the book we are writing with the TAC and Lee. Okay, our next result gives sufficient condition for mu topological stability. Okay, to begin with, you need example here, example of mu topological J stable for a given mu. Okay, the idea is this. We are going to see the suppose it's expansive. Okay, the first of all, you see, expansive plus shadowing already implies GH topological stability, and therefore, because GH topological stability implies that every mu is topologically stable, then you have examples already. For instance, when expansive plus shadowing, you already have the mu topological stability for every mu. Okay, but here I will insist in expansivity. This is the traditional definition of expansivity. Indeed, positively expansive. But here we are not talking about omeo, so I will skip the positively name. And then this is the expansivity definition. And but here I will consider a new notion of shadowing, which is this one for measure, which is called mu weak mu topological shadowing property, which requires that a big set where you can. This is a big set, the view D. The traditional shadowing say that for every epsilon there is delta, so that every delta pseudo-orbit can be epsilon shadowed. But here I will not require every delta pseudo-orbit, but only those which pass through a big set here. And the big set is this, and this set the meaning of big set is that the measure of the complement is very small. Okay, this is the definition of a weak mu shadowing property. Of course, these do not imply not easy to see, of course, but the example is not so easy, but first of all, mu shadowing property implies weak mu shadowing property, but the compare is false. Okay, so you don't necessarily have a mu shadowing from weak mu shadow. Okay. Now the theorem 2 is this stability theorem. Suppose you have a compartmented space, you have probability measure, and suppose that you have a expansive map with the weak mu shadowing property, and therefore this map is mu topological stable. Okay. About the proof of the theorem. Okay. The first theorem have 4 items. The first item is very easy. You have this estimate. This estimate for you give to you the definiteness of the distance, and the distance 0 when they are measured preserving is very obvious. Now the converse use some approximation by epsilon isometries. This is a standard Arcela-Ascoli approach. We use here an Arcela-Ascoli approach. Arcela-Ascoli argument, not approach. Okay. You see, you have 1 over n epsilon isometries, Jn, and satisfying this rule and this rule. And then you can take a limit. And this limit of 1 over n epsilon isometries, 1 over n isometries, will convert to a genuine isometry. Okay, this is the content of this lemma in the Villani book. This is the Villani book. And and here you can pass to the limit here. You pass to the limit to get this identity. Okay. And the conjugation rule, you pass to the limit this expression. Okay, so no difficult. This is item 1. For item 2 is more elaborated, but it's straightforward anyway. This is a play between epsilon and deltas. Okay, I will not put the detail here. I will skip this part because this is a triangle inequality many times applied. Okay, now I will, this is item 3 here, but it's indeed item 4. The item 3 is the symmetry, which is very obvious because of the definition. Okay, for the proof of theorem B, which is more interesting, you start with the expansive with mu shadowing property. Okay, I will follow the lines of the Walter theorem, but here I have to do some modification because of the complexity of the situation. Well, we are going to fix epsilon and this number in between, where E is the passivity constant. For this A prime, we are let delta and the Borelian given from the weak mu shadowing property. This Borelian, I will assume this inequalities is no problem because I can string delta to get that. Okay, and I will take a G for which this distance is less than delta. Then those by definition you have this delta isometry doing this and this. Okay. Now I go to define B prime. This is the B prime. B prime I define by the pre-image using this delta isometry. I will take a pre-image here to get the B prime, and this gives to you this computation. Here this is the goal of the use of the total variation distance. The total variation distance here very convenient. Here it looks to be a mistake here. Yeah. A kind of a misprint here, but no problem. I correct here. Okay, so I will get this B prime is very high measure because of this identity. Okay, now I want to define the G orbit. Once I get B prime, I will consider the G orbit B prime. We give to you this. This is the definition of the G orbit. You take the iterate of B prime, and then you are going now you are going to define a map, the map H. The map H will be up to this is an approach we do with my paper with Professor. Okay, tenemos Professor Q and Professor Lee. Professor Q, in Portuguese, not very good name, but anyway. Okay. Now, the approach, this is the Professor Q and Professor Lee paper with me. I will do this approach. And this approach, okay, you consider this sequence. This is the traditional, you get V prime from this is, you get some element here. This element theta is have this form for some n theta and some B prime. For this B prime, I will put here, this B prime, I will consider this sequence. This is a sequence, and I will prove this sequence is a delta pseudo-orbit. This is the computation made here. This computation is beneficial because of the distance is zero between. The conjugation rule here is fundamental to get the distance less than delta, which characterizes the delta pseudo-orbit. And therefore, you will have y, the orbit of y according to f, will accompany the orbit of this sequence we defined it before. And then we can define the h of theta equal fn of y. This gives to you a map from h from the orbit to x. This I need to put the closure here, but the closure, first of all, I will you have to prove it's well defined because you have many choices to define this h, and this is done using the expansivity. The expansivity concept, okay, this is played a role here, the expansivity, okay, and okay, now using also the expansivity, okay, you can stop here, and you will okay, you will get this identity, and okay. Now you in the previous you will get this conjugation only in the orbit, not in the closure, because I need to be closed, compact. I need this guy compact, but I will pass to the closure here soon. How I will go there? I will get this because I will prove this is H. This map H is uniform continuous. And this is a trick which is come from the lemma 2 in Walter's paper. This lemma 2 will allow to get some uniform continuity of the map H. When we get this uniform continuity of the map H, which is down here with the trick and the Walter's lemma 2, we are going to prove the assertion that is uniform continuous, and therefore you can. This map extends to the closure to get a map H, which is our conjugation. Okay, the conjugation rule appears because of continuity. You can pass to this identity here, which you have this identity only in H, this identity only in the orbit of P prime. Then you can pass to the limit to get this identity in the whole y prime, which is the closure of the orbit of B prime. Okay, now you can measure the y prime. How big is y prime? You do this computation. With this computation, you will get, because the idea is that y prime contains B prime, and therefore the measure of y prime is very big also. This completes the proof of the theorem. Okay. Now the reference here, I will put some reference, which I emphasize my forthcoming book with Professor Ji-Hun Lee, and also I emphasize also my paper with Professor Lee about the almost observable measure, where we separate. I mean, we introduce the notion of weak new shadowing property for maps. Okay, I also emphasize the Villani book, which I get many sources from here. This is plenty, very good book to do, very good reference about that. And also, of course, the traditional and the classical paper of Walter about where he proved the stability, his stability theory. Okay, thank you very much for your attention.
Gracias, profesor Morales, por su exposición. Consulta, hay un espacio de consulta para los participantes. ¿Alguna consulta? ¿Comentario? Bueno, nada, hasta acá. Bueno, terminamos agradeciendo al profesor Morales por su exposición.
Bueno,
Gracias, profesor.
gracias a ti por la invitación y a Bernardo por no preguntar. Bueno, sí, muchas gracias a los organizadores por la invitación. Espero poderlos ver pronto, especialmente a ti, Bernardo, que ¿no? Te ves con mucho frío, sí, es verdad, parece que tienes mucho frío.